Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In the previous lectures, we have seen how there were several experiments which could not be explained with the existing knowledge in classical physics, and how Max Planck, Einstein and Bohr used new ideas to explain those experiments related to black body radiation, photoelectric effect and hydrogen atoms emission spectrum. The key ideas that they put forward were that the energy levels, the energy of light, the energy of the black body oscillator, angular momentum of the electron, they all were so called quantized. They could not take any continuous value, rather there were some allowed discrete values that these quantities can take. So, this quantization was a new concept that was introduced by these theories. After that, we also saw that like light had both wave and particle like nature, de Broglie's hypothesis suggested that even matter, which is normally considered as a particle, also has a wave like nature. So, this brought forward even another idea, that is the wave particle duality. The consequence of wave particle duality was described by Heisenberg in his famous uncertainty principle, which said that there are some observables like position and momentum that you cannot simultaneously and precisely determine. There will always be an inherent uncertainty in the determination of some variables like position and momentum. So, what we see is that not only the existing classical physics knowledge was inadequate to explain the experimental observations, but also the language, the vocabulary that was in use, that also needed a revision. So, after the progress of quantum mechanics by many other scientists, some of their work we discussed in our earlier lectures. After all these works, it was realized that perhaps it is now time to go back and look at what all new developments have occurred and formulate a new language, a new set of rules, a new set of grammar, so to speak, so that we all can converse easily in that language and communicate effectively in that language. In today's class, as well as in a few more classes from now on, we will spend some time in learning that language, learning those vocabularies, so that we can communicate quantum mechanics to each other freely. So, this is best described in terms of principles and postulates of quantum mechanics. This is the central theme of today's discussion. When we looked at classical mechanics, we see that suppose I have a particle in 3-dimensional space, I have x, y, z coordinate, and I have got this particle here whose position I know x, y, z, and I can also know its momentum p x, p y, p z at a given point of time. If I know the position and momentum of this particle at a given point of time, I can, using classical Newtonian mechanics, I can determine its position and momentum at any future time. But when I translate this concept to quantum mechanics, we immediately see a problem. What is the problem? That in this case, we have defined both position and momentum of the particle exactly, precisely, and quantum mechanics forbids us to do that. So, therefore, we have to now introduce some new concepts as to how we can describe the state of this particle without violating the basic principles of quantum mechanics. This is given by the first postulate, which suggests, which simply tells that the state of a quantum mechanical system, if we want to explain or describe any system through quantum mechanics, the state of that system is completely specified by the wave function. The key operative words here are completely specified, and a new term that we are quantum mechanics allows us to use is the wave function, also sometimes called as state function. This state function, mark the word, completely specifies the state of the system. In other words, everything that is there for us to need to know about the system is out there in this state function that we generally describe as the symbol psi. The psi symbol is simply y in Greek. So, this wave function, or also called as state function, also known as state function, psi is a function of coordinates r, and it is defined at a particular time. But since we have defined the position of it, we cannot explicitly determine declare the momentum of this system, because that will be in violation of the principles of quantum mechanics. But the wave function, the state function psi, contains everything that we can possibly need to know about this system. Then the question arises, what does this wave function or the state function mean? If it has all the information in it, what does it mean? The answer to that, unfortunately, is that there is no physical meaning or physical significance that one can assign to this wave function. The wave function is a mathematical construct that contains all the information about the system, but we cannot provide a physical interpretation to it. However, there exists another quantity related to the wave function which has a physical significance or which has a physical interpretation, and this is called Born interpretation. Born interpretation tells that if the wave function of the particle is psi of RT, this quantity psi star, which is simply the complex conjugate of the wave function, the complex conjugate of the wave function psi star and the wave function itself psi, the product of this psi star psi, this refers to the probability density of the particle at the position r at given time t. So, although psi, the wave function, does not have any physical meaning, what has a physical meaning is the psi quantity psi star psi. This has got a probabilistic meaning which says that at position r at time t, the probability density is given by psi star psi. The other quantity that is also useful is that psi star psi with a volume integral d tau. This volume integral d tau is simply in Cartesian space dx, dy, dz. So, it is together these two quantities says that what is the probability of finding the particle or finding the system which is given, which is described by the state function psi, what is the probability of finding this system in an infinitesimally small volume of d tau. That is a probability. Now, if I integrate this quantity over the entire volume, that I go from minus infinite to plus infinite, what I see is that the total probability of to find the system anywhere in the universe. Since this is a probability, either the system exists or it does not. If it exists, if I search for it in the entire universe, there is always a chance that I will find it somewhere, right. So, therefore, when I interpret my state function in the language of probability, therefore, this quantity, when I integrate psi star psi over all the volume available to me over the entire universe, so the particle will exist somewhere. So, therefore, this net probability is 1. I can make it 1. So, this suggests that the particle does indeed exist. Now, not necessarily all the time the wave function that we have would have this kind of feature, that when I integrate it over all space, I would get the result as 1. In that case, I can actually rewrite my wave function in such a way that this equation will hold good, and this procedure is called normalization. Normalization procedure ensures that the particle exists somewhere in the universe and its net total probability of finding it somewhere in the universe is 1. The next question arises is that how can we normalize a function? This is what we would learn next. We will take a few examples. Let us say first example that we let us take as let my wave function psi be a function of x alone, and I define this function as a sine function, and we would also see this kind of function in our future classes. So, this is sine pi x divided by L. L is some with the length dimension, some quantity with the dimension of length. This is this function exists only for a certain value of x. Only when x is between 0 and L, this is the wave function, the state function is given by this sine function. Otherwise, this function is 0. So, the function is a sine function only when x is between 0 and L, and at all other places, that means x from minus infinity to 0 as well as from L to plus infinite, the state function is 0. Now, the question is that I want to normalize it. How would I normalize? I know that to normalize a function, what I should do is that I should have, if the function were already normalized, I would have this situation. If I integrate it over all space between from minus infinity to plus infinity, I should have 1. However, I am not sure whether this function is normalized or not. So, I am declaring that okay, if psi x is not normalized on its own, so let us say I have a factor n that I multiply it to psi x such that the new function, this is normalized function. Now, of course, I do not know what is n, and that is the problem that I have to solve. I have to find the value of n such that when n is multiplied to this wave function and I put this equation over after that, then the overall integral should become 1. So, now I am replacing psi with n psi, and psi star would be n star psi. So, n star and n it would become n square, and since n will be a constant of x. So, therefore, I can take it out of my integration. So, I have n square. So, psi is sine pi x by L. Psi star, since this function is a real function, its complex conjugate is itself. So, sine square pi x by L dx. However, one more important thing that we should notice here is that I have used my the limit of integration from minus infinity to plus infinity, but actually this wave function exists only between 0 and L. Outside this region, the wave function is 0. So, therefore, when I integrate that function, the square of that, so this is a 0 function. So, therefore, I need not take those regions. So, I will make a correction to what I wrote here. So, instead of using minus infinite to plus infinite, I will restrict my integration only to 0 between 0 and L, because outside this region anyway the wave function does not exist. So, this quantity has to become 1. Now, I would now solve this problem. So, I will look at the left hand side of the problem. I see n square. I rewrite the sine square function as 1 minus cosine 2 theta divided by 2, and when I solve this, I have 2 in 1 by 2 dx minus 1 by 2 cosine, and this is 0 to L. I put these two terms in this bracket. When you look at the first term, I will continue our discussion here. When you look at the first term, you see that it is simply L by 2 minus, when you look at the second term, half. When I integrate this cosine function, I have and this I have to calculate at two different limits, 0 and L. When I, so the first term is easy. I now look at the second term over here. When I put x as L, I see this is sin 2 pi, which is 0, and when I put x as 0, then I see sin 0, which is again 0. So the second term in this would be 0 minus 0, therefore I get 0, and I am left with n square into L by 2. But I know the value of this should become 1. So therefore I say that n square into L by 2 is 1, and what is the value of n? That is, so now I obtain the so called normalization constant, which is 2 by L under square root. If I multiply this normalization constant to this wave function that I started with, then that wave function will be normalized. So this is my wave function before normalization, and the wave function after normalization is simply now this is how we normalize this function. So here in this case we have the function as a real function. So therefore the complex conjugate of this function is itself. Now we will look at another function and see how to normalize that. So the second example that we will take is, let us say the wave function, the state function is given as e to the power I phi, where phi is somewhere between 0 and 2 pi. You can imagine that the phi is that the angle when the on a circle that goes from 0 to 2 pi. Okay, so I have this wave function and I want to normalize this wave function. Again, I use a normal to normalize it, I have to set the limit is 0 to 2 pi, because this is where the phi is this is how phi is defined. So it is the entire space that is available to the system. So in the previous example, when we had x coordinate as the dimension along which the system was moving, so therefore x could go from minus infinite to plus infinite. However, since this is an angular coordinate now phi, whose limit is between 0 and 2 pi. So we are the entire space available to us is between 0 and 2 pi. So if psi is the wave function that is given is e to the power I phi, then exponential function, you know the complex conjugate of this function will be e to the power minus I phi and then the wave function itself. And when I multiply these two quantities, of course I get 1 and when I solve this, I would simply have n square into 2 pi. But if the wave function is normalized, I know after normalization this value should have become 1. That is what the normalization means, that the probability of finding the system anywhere in the universe is 1. So n square into 2 pi is 1. So therefore I get my n as, so this is the normalization constant for this wave function, and this wave function is before normalization. If I have to write the normalized wave function, I would simply write this. So this is now my normalized wave function. My wave function is now normalized, so that if I integrate it over all available space, then the integral would give me 1. This is how I would normalize. Now, as we discussed, the wave function itself does not have any physical meaning, but its psi star psi, the complex conjugate and of the wave function multiplied by the wave function itself has a probabilistic meaning. Since the wave function does not have any meaning, so we need not worry about what kind of behavior the wave function would have. However, since the wave function square or the psi star psi has a probabilistic meaning, so therefore, that interpretation imposes some additional conditions on the nature of the wave function that we can have. So, this is what we would discuss next, is that we expect that there should be some particular behavior should be there for the wave function before we can call that that's actually that qualifies as a state function, or it is an acceptable function to describe the state of the system. What they could be? For example, the wave function must always be single valued. Why so? Because if wave function is not single valued, then the square of the wave function again would have multiple values, and the square of the psi star psi, if that has multiple values, then we have a problem, because psi star psi represents the probability. So, if the probability, so if the psi star psi is a double valued function, then we will have a problem that we can say that at a given at a given point we have two different probabilities of finding the system, and that is absurd. So, therefore, we will ensure that the wave function is single valued. The second condition that we would impose is that we see that the we should always be able to normalize the wave function, because only by normalizing we ensure that there is the total probability of finding the system anywhere in the universe is 1. So, therefore, normalization is an essential criterion to have in a wave function. So, we should have a state function, or we should have a wave function such that we should be able to normalize that. But we see when we are normalizing them, we are essentially calculating a square integral. So, the wave function therefore must be square integrable, and we know when I am integrating a function, I am essentially calculating the area under the curve. So, if the function is square integrable, so that means the function should always be continuous. What if it is not continuous? Because if the function is not continuous, then I cannot calculate the area under that curve. So, therefore, the normalization procedure will not be complete, right. So, therefore, the wave function must be continuous. Also, its first derivative must be continuous, although at some point in time this criteria is sometimes relaxed. The other condition that we must impose on the wave function is that it should not become infinite over a finite interval, because if it becomes infinite, the wave function, then its probability also becomes infinite, and if I have a function which is already infinite, I can never normalize that to 1. So, therefore, these are some of the essential conditions that we impose on our system to before we call that their acceptable function or well behaved wave function. So, these qualities are essential for the wave function to be called well behaved, or sometimes we also say acceptable. Now, what we will do is that we will look at a few examples and discuss that whether this function is acceptable or not. The function that you see here, the x axis is shown here, the wave function psi is plotted. So, this is a plot of psi against x. Let us see what features this wave function satisfies and what feature it does not. For example, if we see that we will go from the bottom. Is it infinite over any finite interval? It does not look like that, because at both limit, when x goes to plus infinite or when x goes to minus infinite, the wave function appears to go to 0. So, therefore, and within this region the wave function is not becoming infinite. So, therefore, the wave function is not infinite over any finite interval. So, this condition is satisfied. Is the function continuous, and is its first derivative continuous? It is so, because the wave function is all along continuous, and if you look at its first derivative, which is essentially the gradient of the function, that also would be continuous. But one thing that is not satisfied here, that you can already see, is that the wave function is not single valued. Let us see here. For example, if I take this point in x, I see what is the value of psi at this point. I can see that I can have 3 different values of psi for a given value of x at this point. So, 1, 2, 3. So, therefore, this is not single valued function and this is not an acceptable function. We will take another example. As you can see here, the wave function goes to 0 on both the limits. So, but one critical condition that it does not satisfy is that within this region the wave function is not continuous. So, that there is a discontinuity in the wave function. So, therefore, this is also not an acceptable wave function. We look one more example. In this example, you see that the wave function, when it is minus infinite, the wave function becomes 0. But as you go in the positive direction, this wave function it simply shows that it is going up and up and up. If it goes to x equals infinite, this function will become infinite. So, therefore, there will always be a finite interval when x is very large, where then this function will become infinite. So, therefore, if this is the nature of this wave function which goes all the way up as I increase x, so therefore, this function also is not an acceptable function. However, if I change the limit, if I say no, do not worry about what happens to the wave function after this value. So, if I restrict the limit of my wave function between this and this value of x, then this function is all right, because in that case the function is bound and I can calculate the area under this curve. So, but as a whole, if I define my limit as minus infinite to infinite, then this function is not acceptable. Let us look at these two functions. First, we would consider this function. If you see this function satisfies all the criteria. It is single valued all along, the function is continuous. If you calculate the first derivative is also continuous all over, and it is never infinite over a finite interval. On the other hand, when you look at this function is single valued, that is all right. This is continuous. It is not infinite over any finite interval. However, the first derivative is not continuous, because this wave function shows a cusp like behavior at this region. So, here the first derivative is not continuous, but in some examples you would see that this is still an acceptable wave function. This is called that this is well behaved in piecewise manner. But such details we would discuss more when appropriate systems come into our hand. So, in today's lecture, we discussed the first postulate of quantum mechanics, which said that there exists a state function for the quantum mechanical system that contains all the information about this system, and this wave function does not have any physical interpretation. However, the psi star psi, the complex conjugate of the wave function multiplied by the wave function itself, has a physical meaning, and this was given by Max Born, the so called Born interpretation, which gives a probabilistic idea for the wave function. Now, since psi star psi has a meaning, has a physical definition, therefore, we imposed some necessary conditions for the wave functions to have before we call this as a well behaved function. We will continue our discussion on other postulates of quantum mechanics in our next classes. Thank you very much.